So in the last video we finished here the layout of PMOS, but I missed one thing. We made the contact between these two things, but it didn't connect a metal layer between these two things. So go here and select metal, then click on this, then press R, connect both of these things with a metal. Same way we can connect this thing also using a metal. Press R. Okay, now this form the complete PMOS. So here we have connected these two drain and N well with a metal. The same way, if it is PMOS, NMOS, for example, I'll show this thing. This should be an N select. And here you should have a P select. Press R. Okay, now we have connected the source of the NMOS with the bulk of the P substrate using a metal. Already we made contact here. Over that you make the metal connection. So these two now will be physically connected. Okay, and now we will see how we can draw an inverter which is having a width of 3.6 micro and length 0.6 micro for NMOS, and for PMOS 7.2 micro. Width and length is 0.6 micro. So this is the basic transistor structure I have, which is having 1.8 micro width and 0.6 micro length. So I want to make 3.6 micro. So what I can do is, you press here, okay, select this point, then left click, hold it, then drag, then release it. Now this enter portion is selected. Now you press C, then move it. C means copy. Now this forms a transistor with 3.6 micro width and 0.6 micro length. Now I want to make a PMOS of a length 0.6 micro and a width 7.2 micro. So what I can do is go here, again left click, hold it, select this, then press C. Now entire thing is selected. Now you keep 12 units away from this active. Okay, that is the design rule, 12 unit. So actually I know that thing, that's why I am using that, or else you can take something more than that, no problem, but it should not be less than 12 units. So I am taking somewhere here. Okay, 1 2 3 4 into 4 16, that is enough. Okay, I placed this thing here. Now again go here, press C, so entire thing will be selected, place it here. Now I have this length is 7.2 micro, that is the width of the PMOS, and here I have 3.6 micro, that is the width of NMOS. Now this is not completed. What we want to do is, we want to make the implant. So go for N select, press R, select a point, then press R, Okay, so then go for P select, press R. Okay, now the thing is not completed. Why? Means we have not yet made a connection between the bulk and the source of this transistor. So how you can make it? By a metal layer. Go here, go to metal one drawing, select it, press here, click on that, press R, then make the metal connection. Now again here, press R, make the metal connection. Now our entire NMOS is completely ready. Now go to PMOS, then again metal 1, because we want to connect the N well and the drain. So all this entire thing you selected. Now go here, press R, entire thing is selected. Okay, now one more thing is, two more things are missing. Select layer, select, go here, press R, P select. Okay, now go here and select, press R and select. Now N well, we have to keep the N well here. I'm just zooming this. Now 1 2 3 4 1 2 3 4 5 6 unit will be here, and R, just go here, select N well, 1 2 3 4 5 6, press R. Okay, selected that thing also. N well is ready. Now NMOS and PMOS are ready with 3.6 micro width and 7.2 micro width as for PMOS. Now we want to make all the connection. Gate of this one should be connected to gate of the NMOS. Go here, click poly, select this point, press R. Okay, that is connected. Now metal 1 is taken. These two things should be connected. Press R. Source of drain of the PMOS should be connected to drain of the NMOS. Make that connection. Then press here, press R. This is the output connection. Now press R. This is the connection for VDD. Now ground. Press R. This is the connection for VDD. This is the connection for ground. Now we have to make a connection for the input. So for that, take poly, go somewhere here, press R, make some connection like this. Then poly is there, we extended that poly. Now if you want to have a connection between the poly and metal, we want to use a poly to metal contact. Then only you can use the metal over that poly. So go here, press R, okay, with 2x2 unit M, placing here at the center. Okay, now go here, take metal R, this now act as the input. After that you just go here and verify whether our DRC rules are right. So that file is already there, click OK, and it is showing no DRC errors found. So our design is good. Now here you want to make pin connections, name to the pin we want to give. For that purpose, go here, take metal 1. Since this is metal 1, go here, take metal 1, press here, then press T, the button T on the keyboard. Then this window will appear, write V pos, voltage positive. Okay, click there. Now again click metal 1 pin, go here, click T, that is V in. Okay, place it somewhere here. Then again metal 1 pin, click here, T, V neg. Then again metal 1, click here, press T, this is now V out. Okay, click here. Now enter pin connection is also ready. Now we go here, verify tool, extract, run. Now we are going to extract our circuit. Run LPE and take the extract LVS file, open, then give OK. Now extracting most devices, extraction completed. So the extraction have completed. Now go to file, export, and export CDL. Then we are now exporting our CDL file. That this information we will get in the extracted file, that is the CDL file. And click on this where we want to save that file location you give. For me it should be inside the result, so I am writing inverter dot CDL. Okay, now save it, give OK. So it will generate the CDL file that has been generated. Now go and open our LT Spice file, open, and see that go here, all files. Now that CDL file is here, inverter.cdl. I am trying to open that, open it. So it is showing inverter is the name, and it is having 4 pins, V in, V neg, V pos, V out, and MM1, MM0 are the 2 transistors with this technology, and one is having 7.2 micro width and the other have 0.6 micro, 3.6 micro and 0.6 micro. That is the required one. Actually we designed for 3.8, 7.2, same thing it is showing. Now select this portion and right click, then it will appear create symbol, click on this, click yes. I already have that named files, that's why it is coming, otherwise it won't come here. Yes, now it generated a symbol, a sub-circuit symbol for my inverter. Now go here, file, save as. I am going to save this file in my result again. So save it. Now you can close this. Now I have made this file from my CDL file. Okay, I have not yet made a schematic. So now go here, file, open, extraction dot. This is the file I already made. If you actually want to make, go to file, new schematic, and make every setup like this. Now because I have a for saving time, I have made all these things. Dot means this is for measuring the propagation delay. Okay, so go to components. Now go to components, go here, go to result. Now that inverter has K, click OK. This is the symbol I generated from our extracted file. Okay, extracted file of the inverter. Now V positive is connected to VDD, that is 5 volt, and V in is to be connected to my input source, that is a pulse of 10 nanosecond, 10 nanosecond. These are the rise and fall time. 5 micro is the on time and 10 micro is the period. Okay, next I'm showing here how you can create the circuit directly from the extracted file and how you can simulate that thing. Now I'm going to make 2 pins. One is V out, that is the output pin. Okay, and the other one is V in, that is the input pin. Why I am going for this is, I will show that thing, why I make this V in and V out, because see here in my dot means directive I have used V in and V out. So these two things should come from the measurement window. To have that V in and V out, I can have V in and V out here. Otherwise it will show some 002, 001 like that node value. To avoid that, I used V in and V out. Now I am going to run this file. You add dot include Glade that dot sub, because this have NMOS, C5 NMOS and C5 PMOS. So to get that value, you use this sub file. Now run it. Now we will show. See, I will show you. This is V in. What is V out? It is the inverted wave. Now I go to view and go to spice error log. Now see my TPDR. The propagation delay is 643 picosecond. 643 picosecond is my propagation delay. So 643 picosecond is the propagation delay of my extracted schematic. That means that is the delay of my post layout simulation. After layout, from using that layout information, I am getting 643 picosecond. Now we will see what is the value without this extracted information. For that thing, I have already made that setup ready. Go to ESC. You just draw that thing. See, I have made 2 transistors and given the name of our technology, and I will show. One is 0.6 and 7.2 and the other one is 0.6 and 3.6. I have made the same pulses 0, 50 and 10 nanosecond and 10 nanosecond for rise and fall. 5 micro is the on, 10 micro is the period, and at 2.5 and 2.5 V in, V out. So I have taken V in, V out. 5 volt is the applied voltage, and same file I am using. Now I run it. Now we will see. So Vin is there, Vout is there. Our aim is to measure the propagation delay. What is the propagation delay? So go to spice error log. Now it is showing the propagation delay 467 picosecond. This is the result we are getting only by using our model file, but we are getting 640 picosecond as the new delay after the post layout simulation. We are gathering the information from layout, so it is including some of the parasitic capacitance into effect. So we are getting 640 picosecond as propagation delay, but without that we are getting 467 picosecond. Okay. And one more thing I would like to say is, if you want to draw a capacitor or inductor, capacitor or a resistor, what you can do is, if you want to draw poly to poly cap, you take one poly here like this and draw it. Take R and draw it. Then we take poly 2, again draw it, poly 2. In between that you have dielectric. Now this tool cannot understand you mean it for a capacitor. So in order to give that information to the tool, you can see here cap ID. So select that cap ID and your active area for this capacitor, press R and cap R and draw it. Okay, now this tool will understand you mean it as a capacitor. The same way, if you want resistor, draw something like this. I mean, if I use res and if I place here R, now it will take it as a resistor in this area. So in your extracted file, it will give you the information like some resistor value is also there at the output. Just check it. Okay, thank you.